This is a just-in-time lecture, and so I apologize for being such a nerd. I'm working on the slides until just right up till this morning. It's new work with a guy named Tiemann Woutersen. It's Dutch, so is it Woutersen? I guess I would say Woutersen from University of Arizona, and it's on using finite mixture models, and so, I'm kind of following the lectures of Victor and Stefan, and, I've kind of checked. I think I'm not overlapping too much, but I think it's complementary, and it fits with the theme of this conference in summer school. So here are the things I'm going to get through. Now, there's actually 111 slides I have. I'm not going to, basically, I won't be able to get through all of those. But a lot of them are like movie. I'm going to play it like some movie. I'm going to click through the slides. It's my low-tech way of doing a movie. So not all of these actually have equations on them. But I'm going to start out by just talking about random effects and fixed effects, just terminologically. What does that mean? How does that relate to heterogeneity? Then I want to talk about the limits to fixed effects, which is called the incidental parameters problem. There's something, a classic article by Kiefer and Wolfowitz. Then I'm going to come back to structural models, and we're going to ask how should randomness enter our models. So we talk about the random utility model, but then there's other things that we think are parameters, preference parameters, like risk aversion or something, right? So we want, but then there's a very confusion. There's a new class of models called random preference models, where the risk aversion is actually a random variable. So we'll talk a little bit about that. Then I'm going to talk about a paper by Jeremy Fox, Stephen Ryan, and Papayari called The Random Coefficient, and there's another co-author I forgot. I always forget that other co-author, called The Random Coefficients Logit Model is Identified. Now, I thought that's a very bold title, and that kind of got me, like 4 years ago, I started looking at this, and what I'm going to argue to you is that there's a difference between theoretical identification and practical identification as an applied person. And what I'm going to argue is I have a negative or basically a not so good message, which is trying to learn about unobserved heterogeneity is really, really hard. It helps when you have panel data, but it's almost impossible or very, very difficult if you only have cross-sectional data. So having panel data, the more panel data you have, the better you can. But the good message is that finite mixture models are like super good approximations. So one of the things that we'll talk about, it's been found over and over, when you estimate these finite mixture models on unobserved heterogeneity, they typically only find 2 or 3 types. People always say, yeah, at the conference, people were showing me results. They say, I found 2 or 3 types. And you say, really? There's got to be more than 2 or 3 types in reality, right? There's got to be a continuum of types. Why do these models only always find 2 or 3 types? Well, we think we have an explanation for it, and it comes down to results in neural networks, and that certain neural networks are, so basically a finite mixture model is a kind of neural network, and an approximation bounds show that these neural networks break a curse of dimensionality, and with very few hidden units, which are going to turn out to be the types, these neural networks provide a really good approximation to the CCPs, which is really where the likelihood is based. So that's kind of the outline, and then I'll talk about then how do we handle not only, so far it's been only unobserved heterogeneity. What if we have observed how do we account for both of them? Now, Bertel in his lecture, we're talking about our auto problem, and we had 8 types, right? It was like urban, rural, single, married, what was the other one? Yeah, far and So we had 8 types, but man, it made a huge difference. So in some sense, they say it's always better to have observed heterogeneity than unobserved, but probably you want both, right? So we probably would say for our model, within these 8 types, there's further unobserved types that we'd like to learn about. And the good news is in these structural models, maybe we don't need 1 billion types. If we're solving the equilibrium in the triple loop, like Bertel's saying, If we could get away with two unobserved types for each observed type, then we'd have to only estimate 16 dynamic equilibrium per loop. That, and if the 2 already provides a really good approximation, well, that's really good news for us, okay? So it's very good. So that's the good news, yeah. Yeah, Rasmus.
So that's probably good news if you don't actually care about the heterogeneity per se.
That's right.
Because it does seem to suggest that suppose you know you have 8 types. When you see them, they seem to be significantly different from each other. You take them away, you're saying you're going to find that there are 3 or 4. So you can actually rely on these discrete mixtures as your message to tease out the data.
That's true. So, we're going to come back to that. We're going to show that the rate of convergence to the true distribution of unobserved heterogeneity, which may be observed, oh, that's my computer, I bet, yeah, there we go, is very, very slow. The more panel data that you're going to do better, but it's very, we'll show you some examples where it's just hard to infer. In other words, it's a hard problem. So, basically, you can explain well with a small number of types. So I'll try to convince you that. So then there's a number of cool empirical applications. I probably won't have time to go through all or maybe any of these, but I put all these in the Dropbox. And, one is a paper I'm working on with my grad students, and it's a reanalysis of a paper called Are People Bayesian? Where basically it's asking, do humans follow Bayes' rule? And in the original study by Elgamal and Grether in 1995, JASA, kind of found there was 2 types. There was one type that were like, they follow Bayes' rule kind of, like noisy Bayesians. And then the other type were people who follow the representative criterion, Kahneman and Tversky of the behavioral literature. So they have a behavioral type and a Bayes type, right? And so then there's another paper just came out in the JP by Tomas Jagielka, and it's a model of using experimental data to estimate time preferences and risk aversion, and they relate it to what's called the Big 5 like if you're more risk averse, are more conscientious people more or risk averse, for instance, right? And so it's kind of a cool. Some people think, oh, the psychology is just total BS, but I actually think it's kind of cool where they can break down observed and unobserved heterogeneity and see how much of the heterogeneity can we explain with observables and how much remains unobserved. Okay, and then an even cooler paper is Chen Jung was a student I advised who's now at Morgan Stanley. But this is a super cool study. I definitely should take a look at this. This is, he's got data from an Asian online shopping mall. You go online, and he's looking just at smartphones. He's got hundreds of millions of observations. But like any website, you don't know the X's. You don't know if they're male or female. But he's got the click stream. He knows the entire click stream till when you start searching to when you put a phone in the basket and you check out or maybe leave the site. And so just using that, he can tell a huge amount about heterogeneous purchases and who buys what kinds of smartphones. And he's using deep neural net, recurrent neural networks to uncover both observed and unobserved types in this, and he generates very realistic cross-price elasticities for smart and search behavior for smartphones. So it's very, very cool. Then Pranjal is another student at Georgetown. He got data from H&M, the female clothing place, and he's got digitized of dresses, and he processes the digitized version of the dresses through a filter using a neural net to come up with, quote, attributes of dresses. So he can see different colors and styles, and then he interacts that with heterogeneous characteristics of the people buying dresses. And the model can predict, like older women like more mature dresses and younger women like, shorter skirts and more, flashy dresses. And you see automatically, this thing automatically characterizes different people based on their preferences and what their substitution patterns are. Very, very cool. So, and then I have a paper on bidding strategies where I don't want to talk about that now. So, so fixed or random effects. I always find these terms kind of really annoying. I think reduced form econometricians and statisticians, they just love these terms, but I find them very confusing because people, you know, they throw a lot of terms and you just nod your head, oh yeah, that's a random effect, that's a fixed effect, you know. I was really gratified. I looked at this article. It was a pretty famous statistician at Columbia named Andrew Gelman. He wrote an article in 2005 in Annals of Statistics, and he says a persistent point of conflict in the analysis of variance literature is the appropriate use of fixed or random effect. And then he goes on to give 5 different definitions of fixed and random effects that are used in the literature. So I think it's important just to be careful terminologically, you know, like what is a random effect? What is a fixed effect, right? We kind of, you know, just the term effect, right? There's a causal effect, but what's a random effect? And what's the difference between a parameter and a random variable, right? And then sometimes we talk about random parameters, and then we have a distribution of random parameters with hyperparameters. Wow, it gets you're totally confused, right? So I'm going to try to be clear, you know, what it is. But normally we think about a parameter is not random, and then there's random variables, and we can estimate the distribution of a random variable with parameters. But oftentimes when we think about, you know, homogeneous preferences, we're estimating your discount rate. That's a parameter, right? Now there could be a distribution over discount factors. So when we estimate each person's discount factor, we can say that's a fixed effects approach. If we put a distribution over that, that's a random effects approach, right? So you're nodding your heads, good. So we're kind of getting there. Now let's just look at the simplest regression model. This is, suppose there's a fixed tau, yi is just a very simple scalar observation. Epsilon is a normally distributed, that's the random part. And then let's think about the tau I is parameters. So that would be like a fixed effects approach. You want to find out the fixed effect for every person and we have panel data. We observe people, T periods, and N people, okay? N independent people, and then let's suppose that the data are, for each person, the shocks are IID over periods. Now, is it obvious that you can't consistently estimate the fixed effects won't work here, right? Unless T is really, really big. So why is that? Can someone explain why can't we consistently estimate the tau I? There's N of them. Well, just think about, we want the number of observations per parameter to go to infinity. Well, if you actually say, well, there's how many parameters, how many observations are there? There's T times N, right? T for each person times N. How many parameters? Well, there's N fixed effects plus sigma squared. So if you divide that, the ratio goes to T. T isn't going to infinity, right? So you don't have, you're not going to get consistency. And this has been observed since Kiefer and Wolfowitz, 1956. And they use this example. Now, what did they do? Well, there's a number of ways that you can handle this. One is to difference out the fixed effects, right? So if you take a difference of the y's, the fixed effects go away, and then you just get the difference in the y's is just going to be a mean zero random variable, and then you could recover sigma squared by those residuals, right? The variance of those residuals. You know, and Victor Garibiria, he talked about a sophisticated way of doing that with discrete choice models, and that kind of idea was really first thought of by Gary Chamberlain, who did this conditioning on a sufficiency. Gary Chamberlain used to be here at Wisconsin, and unfortunately he passed away a number of years ago, but super smart guy. You know, the problem is when you difference stuff out like that, you're throwing the baby out with the bathwater, right? You might want to know what those taus are. If you want to make prediction of what the y is, you need to know what those things are, right? Now, so Kiefer and Wolfowitz didn't propose differencing. They said, let's just directly estimate. We're going to make the parameter a distribution over the tau. And so we're going to, now we have an infinite dimensional parameter, right? You could call it semi-parametric maximum likelihood, because there's a parametric thing, sigma squared, and then there's this entire infinite dimensional, sometimes they call it a nuisance parameter, but sometimes it's the really thing of interest. It's g of tau, that distribution. So then they say, well, let's just formulate a likelihood, which is you integrate out the tau for each person. So you write the conditional distribution of y given tau, and then you integrate or marginalize it out, and now you get a likelihood in these two parameters, the g and the sigma, and they propose just directly, let's just maximize directly over all distribution functions as one of our parameters, right? Now, they prove that that is consistent, but it has to be identified. So you have to assume the model is identified, which means you have to show that if you can explain the same distribution of y two different ways, there's the first one would be, it should be an h here. This should be h and then omega, and if that equals, if the true is sigma and g, then you have to conclude that there's only one solution, that h has to equal g and omega has to equal sigma. So we're going to talk about identity. It's like inverting from what we can observe, the distribution of y, the marginal distribution of y, back to uncover these two pieces. Now, it turns out that you can in some cases and you can't in other cases. Now, one of the cases where you can always do this is you just make g a parametric distribution. And this is still used today, right? Like BLP, they call it random coefficient. Tau is the example of a random coefficient, and they'll assume it's a normal distribution, and then the beta will be the mean and the variance of the normal distribution, right? And then you just estimate those, and now it's an entirely parametric problem. The problem is that the criticism is how do we know these random effects are normal? What if they're not normal, right? So we'd like to do something more semi-parametric or non-parametric. But if you do that, for instance, one of the reasons why do you do this is not just to learn about the unobserved type, the G, but it's also you can get what's called spurious serial correlation, or Heckman talked about spurious duration dependence, right? So in other words, conditional on the tau, so if you assume that G is normally distributed, then you can substitute for the tau, and there's a residual. You can write tau is equal to its mean plus a residual, and now you get this combined residual where this is serially independent, but this is dependent across. So if you look at the covariance, it's going to be, even though conditional on each tau, their choices are independent. If you don't account for it, you're going to look and say, wow, the data are serially correlated, right? And that's just entirely spurious because you haven't controlled for the unobserved heterogeneity. And this appears widely where that's why people use fixed effects and random effects to avoid, those kinds of spurious conclusions. Now, what was observed in Annals of Statistics, a guy named Lindsay, is that if we directly maximize over this infinite dimensional parameter, the CDF, could be any CDF, the solution will actually always be a finite mixture. With finite amount of data, you'll never get a continuous distribution. The maximum likelihood will always be, you're using something called convex duality, and the G that you get out will always be a finite mixture with the number of mixture points no higher than the number of observations in your data set. So you always can find a finite mixture that is literally the maximum likelihood estimator. So, there's no loss in some sense, no loss of generality in restricting to finite mixtures because of Lindsay's result. Okay? Now, the idea is that this becomes what's called a sieve. Finite mixtures is an expanding, we talk about bases for vector spaces and have, approximating in infinite dimensional space. The sieve is it's not like a basis, but it's a collection of expanding parametric distributions, which is called dense. In other words, you can approximate any CDF, whether it's continuous or discrete or mixed, with a finite mixture arbitrarily closely when the number R of mixing points in that distribution is large enough, okay? So that's kind of a basic result in probability theory. Okay, so if you allow R to go to infinity as n goes, so in particular you can let R equals n, then you're going to get consistency. That's what Kiefer and Wolfowitz showed back in 1956. So let me go to the next slide. Now let's just recall some convergence concepts just to understand this. So we remember this called converging weakly or converging distribution. So one way to define that is to say GR converges weakly or in distribution to G if for any continuous function, bounded continuous function G, the expected value of G converges to the expected, under G of R, converges to the expected value of little g under the distribution G. Okay, so that's called weak convergence, and we use this arrow here to denote weak convergence. So when we're thinking about Kiefer and Wolfowitz, the notion of convergence is basically something like, this will be a random CDF, a random mixture, but we're going to say this random mixture converges with probability 1 weakly. It's going to converge in distribution, but it's with probability 1 for all possible data realization. So it's kind of a double concept. Normally when we talk about parameter, we think in Euclidean space it's converging. The Euclidean distance between the true theta star converges to 0. This is the same thing, but the notion of convergence is a little more abstract, convergence and distribution. Now, I have some Russians here, and they can tell me if I pronounce this wrong. It's called Prokhorov. You know, how many people have heard the Prokhorov metric? It's called, this is a little bit, topology, but they talk about we can think of CDFs living in a metric space, and the Prokhorov metric is a distance between G and G of R, such that whenever G of R converges in distribution to G, it's equivalent if and only if the Prokhorov distance between G, R, and G goes to 0. So it's a measure of how close. Now we're going to come back to that. It's going to play a role. Now, it's really actually hard to calculate. This has got a weird definition. It's not really, nobody almost ever uses this metric because it's so hard to calculate. It's just there for kind of theoretical purposes. Now, another notion is a stronger notion, which is like you could call this Kolmogorov-Smirnov distance, right? It's the maximum. This is much more easy to understand. It's the maximum distance, between the G and its finite approximation. Now, this is what we're going to work on this. But the problem is this is a much, so like in, Euclidean space, finite dimension, you could have the L1 norm or the the soup norm or the L2 norm. They all define the same topology over the space. But in CDF land, that's infinite dimensional, this is stronger. You can have something close, far away from G. So this distance can be very big, but the Prokhorov distance can be very small. So they're non-equivalent topologies. So whenever this is small, the Prokhorov distance will automatically be small. But this could be big, but that could be small, okay? So it's going to help explain some of the results, so why it's hard to estimate the distribution of unobserved types. Okay, so that's, I think I'll just go over this now. Now we're going to jump ahead to Heckman and Singer. This is a pretty famous paper, and it was, that's the title. They were focusing in 1984 about estimating like hazard models, like duration of unemployment and so on. And basically, they were very early to appreciate, and others people before them, that you have to have unobserved heterogeneity in these models, or else you can get spurious duration dependence. Like an example would be like you're on unemployment, and the idea is the longer you are on unemployment, you're going to even be, the hazard of getting out of unemployment goes down. And people say, well, that's got to be due to decay of human capital. And people say, no, that's not necessarily the case. You could have everyone's exponential. That's a memoryless process. It's just that there's some people who are really bad apples, and their exponential parameter, they're going to be on unemployment for a very long time, and other people have rapid exit. But when you see the mixture, it's going to look like the longer your unemployment, the lower the chance. So that's spurious. There could be structural duration dependence, but there could be also spurious, and you want to be able to separate them. So that's what Heckman was trying to do in those days. So, so basically, the first question, the answer is, there's some parameters of type tau. This is the duration distribution. T is time, duration of a spell. This is the distribution of unobserved types. And so what we observe in the population is this. And the question, first of all, is can we invert from this? Now, if we allow this to be unknown and this to be unknown, Heckman and Singer said it's impossible. You can't. There's many possible solutions for this and this to equal that. But if you fix that, and this is parametric, this is the non-parametric. So this is an example of early semi-parametric model. They showed that, under pretty general conditions, you can infer this from this. That's identified. There's only one solution to that. There was an earlier result of Elbers and Ritter's, kind of a classic 1982 paper for what's called the proportional hazard model. Yeah, in other words, there's only one solution for any F. There's only one mixing distribution that generates that duration, population average duration distribution. Okay. So, here's an example too where there's two different ways of explaining it. If you don't put restrictions on this, one is that everybody there's no heterogeneity. Everybody has the same population average F of T. No it's homogeneous. The other is there's different types of people tau with this really kind of weird duration distribution here, and then we have a mixing distribution, and the mixture of that and that generates that. So these are two observationally equivalent models that so it shows that you have to put some restrictions somewhere. So if you assume this is the right conditional distribution, then you can identify this, but not otherwise. So we talk about parametric and non-parametric identification. So, the first thing we said, well, what's typically done is assume this is a member of parametric class. Well, once you do that, then this is parametric and this is parametric. And under pretty general conditions, you'll be able to find a theta that is identified. You'll be able to identify a finite, so entirely parametric model now. You have to integrate it. But now the question is non-parametric identification and estimation. And so now we're going to talk about finite mixtures. That's what Heckman and Singer proposed from, borrowing from Lindsay. So now we have, what we're going to estimate are these, we're going to pick a K. Later I switch, I think, to R, so I'm sorry for the switch in notation. But we're going to say there's K unobserved types. They have parameters by this vector here, and the probabilities are these. So now, the idea is this is this sieve, this very this expanding family. They can approximate any distribution. But once we fix K, this model is entirely parametric, right? It's just these parameters and these things right here. So now it's really beautiful. Right? It's like used to call them flexible functional forms. We can approximate, this is a finite mixture. We can approximate anything, and then we just let these things go. So this is how we approximate it. This is in Heckman-Singer's case. We have fixed this model. There's R types. Now I'm switching to R. And then we're estimating the probability, the mixture probabilities, and the types together to best fit the observed population distribution. So, here it is written out. It's a constrained maximum likelihood. We take the density of this, G, the conditional density, and we're maximizing this conditional density. And so there's n independent observations. For each person, we take the mixture of the duration distributions, and these are mixing parameters. There could be other parameters as well that are constant, but let's just keep it simple. Okay, now here's the three findings, and they were very, ahead of the ballgame back in 1984. So the first is that they call it the non-parametric MLE, estimates F very well. Okay, so the population quantity is estimated, and if there's other auxiliary non-heterogeneous parameters, the non-parametric estimates the structure, they call it the structural parameters, very well. This next finding is the number of types is very small, 2, 3, or 4, right? And then finally, they find that the distribution G is poorly estimated. They say for both finite and continuous mixing measures, the non-parametric maximum likely never estimates it very well. This is true even when the samples of size 5,000 are used to generate, this is a Monte Carlo study, non-parametric MLE. So they know the truth, they're generating data from this. It never estimates it very well, okay? Now that's a little bit rich because you're saying, well, we're doing this non-parametric method and it never estimates it very well. Well, that's a clue that this is what's called weak identification, right? I mean, if you can't do it in Monte Carlo, good luck in the real world, right? Now, let's go to the multinomial logit model. So this is a conditional distribution. We've been studying this a lot. This is just a different way of saying, I'm going to say that if you can either, y equals 0 is the outside good. So either it's 1 over this thing, if you choose the outside good. We're going to normalize the outside good to have utility of just 0 with an extreme value error term. Or the other, if it's greater than 0, j equals 1 to j, it's just given this is the classic multinomial logit with the outside good normalized to have a utility of 0. But the other utilities are of the linear parameters, xj times tau. And what you might think about like in IO is there's price. And this is the price sensitivity coefficient that could be random in the population. There could also be an intercept, which is how much you like the good, which could be different for different people, okay? So, and then, and our friend, my thesis advisor, Dan McFadden, the logit model, these will be extreme value. So that's why we get a multinomial logit. But if we assume semi-parametrically these taus come from some mixing distribution, we would like to do that. Now, why do we want to do this? Why do we want to do this? Why is it important? What's the spurious kinds of things we can get? Well, this is going back to BLP and well before that the IIA property of the logit model gives you very unrealistic cross-price elasticity. So if you think about this as a market share, and you take the price of some good J or Y, and you look at the cross, if you work out that formula, it doesn't depend on Y at all. It only depends on J. So that's this property that, you would think that if you have a BMW, that you raise the price of a Mercedes, it should have a bigger effect than if you have like an electric, a Volt, right? The elasticity should be very low for someone who buys the Volt, but if you have a Volvo and a Mercedes, you should have a strong price elasticity. So this model totally gets that wrong. So this is why, Steve Barry and Ariel, say, let's do random coefficients. So if the tau is random, and we say, well, it's random, this is a dimension, this is the mean, and this is a vector of normally distributed residuals with mean 0, then we substitute this in and we get this combined error terms. This is IID over different goods, but now this composite error term will have a correlation, which the strength of that correlation will depend on how close the observed attributes are. So now you can get this more realistic price elasticities because the random coefficients captures the correlation. So that's why we want to do this. Now, let me make a concept, just a aside before I go further into this. In the standard logit model, we're going to think about if we have panel data, tau is a fixed effect for each person, right? There's your price sensitivity doesn't change. You have random utility. There's other things that shock you that that we think of as unobserved states that make you choose one car or another when you're shopping, but your price sensitivity doesn't change. Now there's a more recent work, and there's a paper in 2018 in the JP by Apostiguia and Ballister, which argues that random utility models are kind of stupid. They say they generate non-monotonic behavior, especially like risk aversion. You would think the more risk aversion you have, your chance for choosing a random lottery, the more risk should just go down monotonically. And they can construct example where it's non-monotonic. Well, I think I won't go into it that much. I think that it's a little bit bogus, so I disagree with it. But I think there's a way to answer without going this. But they adopt something called the random parameter model, the random preference RPM model, where your coefficient of risk aversion is just randomly changing every time you choose something. So, I think the most extreme case is the laboratory experiments. You're choosing assumption, and they're assuming that, my coefficient 2 seconds later has changed, and I have a new, so they assume there's IID changes in your risk aversion parameter. I just think that's pretty weird, right? Now, maybe I have limited imagination, but that's what they're doing. And then they say, well, if you have that, you won't have the non-monotonicities. But then you'd say, like, wow, do you really think people are that random? I don't think, there's some randomness, but I don't think people are that random, okay? But, this is something for the future, for empirical work. It could be, I definitely think my preferences have changed since when I was 18. You might have slowly varying preferences over long periods of time, but do they change second to second? Well, I guess that's, for further work.
Does that mean that the utility function is just an integration over?
Yeah. So it means that, there is, when you think about a fixed effect, your preference parameters, there's no, it's a random effect. Your preference parameters are changing every time. They're just random too, right? So then you have to estimate a distribution over your structural parameters that for an individual is random across successive choices. So here's the mixed logit model. The theoretical model would be, there's a kernel, this thing right here. This is the, unfortunately it's a little bit ugly. I should have made it simpler, but this is just a multinomial logit model that depends on tau, and then you're integrating out over tau. And so what you get is this is what Bob Miller calls a CCP, a conditional choice probability. This is the population CCP, and this is the structural or individual specific, and this is a parameter that is fixed for an individual, but it's random in the population. So that's why it's a random effect in the population, but fixed for an individual. Now, with this model, you can get around the IA. In fact, Fan and Train have an article in the Journal of Applied Econometrics in 2000 that's showing that these mixed logits are dense in the sense of all random utility models. In other words, you give me any CCP that's not like from a multivariate normal. Okay, so instead of a logit, you have a multivariate normal. I can approximate it with as closely as you want with a mixed logit. So in some sense, mixed logits are universal approximators. And what you should think about this is, well, there's something called the universal approximation theorem for neural nets. This is going to come back to, this is kind of a neural net. This is like the softmax squashing function, and this is a weight distribution. And so we're going to come back and show this is like a neural net, and this is, what they had done is rediscovered a special case of the universal approximation theorem for neural networks. Now, here we come to this article, Fox, Kim, Ryan, and Biari. So sorry, Kim, I forgot your name there in that. So they have two different proofs of how this works. Why is the random coefficients logit model identified? Well, one is you want to say, suppose there were two different mixing distributions that apply the same CCP here. This is the population CCP. Suppose there are two of them, then you can difference them and you get this equation here, 20, that the difference of this is equal to 0. Now what you just have to show is the only solution to this equation is that this has to be 0. So it looks really obvious. Yeah, it's got to be 0. Well, you know, when these are distribution, this is called a sign. The difference in two CDFs is called a sign measure, and you're not sure whether could there be a non-zero sign measure that somehow really just sets this equal to 0. And the answer is no. There's this paper by Sybenko in 1989 that shows that these squashing functions have a property of being discriminatory. They have some curvature, and they can discriminate. And what he showed is so that any squashing function of this form that's discriminating, the only solution is for this to be 0, i.e. there's only one solution so that the G function is identified. Okay? Now there's a constructive proof. Now the idea here is let's take the binary logit to make it simpler. This is the binary logit case. And what's really cool here is that this is C infinity. It's infinitely differentiable. So you've heard of like the moment generating function, right? You take the moment generating function, you differentiate and you set t equal to 0, and you can construct all the moments, and that's called the moment problem. If you can construct all the moments, you can recover the distribution uniquely. Well, they showed that this is like this function here, the CCP. If you differentiate with respect to x, that's like t. It's like a moment generating function. So if you work out this thing, you can say that if you take the first derivative and set x equal to 0, you're going to get something times the first moment. And the something on the left is known that you can divide out, so you can get the first moment. And then you keep taking derivatives, and you can basically recover all the moments, and from that, you can get the G. Okay? Now, the problem with that is it's really unpractical. You would never want to do this in practice, right? Like, say, let's suppose I non-parametrically estimate this, like with a kernel density, and now I want to take derivatives of all orders. Good luck with that, right? What happens? What do you know about kernel? They're like really wiggly. And also, I'm trying to estimate this thing only at x equals 0. Well, you think about how many data sets do you have where the prices are all 0 or near 0, right? Totally impractical, right? So it's a theoretical, really nice dream. They're really creative, but it's totally useless in practice, right? Totally useless. You never want to use this for, you never want to drive this around in practice. It's like very non-robust. So this is why a more practical is to use a finite mixture. Now, they recognize these, I don't want to be too critical of these guys. They came up with another paper, and it's actually had a big effect. Fox, Kim, and Yang, that's Chenyu Yang at University of Maryland, very smart guy. They're all really smart guys. And they have a simple non-parametric approach to estimating the distribution of random coefficients. And actually, people are using this. Aviv Nivo used it. We'll talk about that in a minute. Now, what do they say? Well, they say pick exogenously a grid over the taus. You just pick a grid. Now, if you pick a grid, then the only parameter left are the p's in the mixing distribution. So this is a mixing distribution of the unobserved types. These are fixed by you ahead of time for a large number of them. And then, you have this list of them. And now you just estimate this. And what they show is that you can estimate this like a regression. So if I think about the multinomial logit model, for each choice, you can write it as a regression with an error term. And the choice probably is the regression function. And so if I get 28, I can think about doing non-linear least square. Actually, it's linear least squares because there's nothing random here. I've already picked that. I'm evaluating this at the data, and that's the data. And I'm just doing this linear regression subject to this constraint here. So it's linear regression subject to a linear constraint. Very, very easy. So it's very appealing to do this. But the problem is, how do you pick this grid? Okay? And I'm saying that's really hard. I mean, if you don't know what the unobserved heterogeneity, you have no clue what they should be. Like, should the price coefficient be minus 10, or should it be minus 1 or minus 0.1, right? How do you know ahead of time? And so to cover your rear end, you're going to want to take a very wide grid. But you also want a very fine grid because the distribution might have a lot of curvature in certain regions. So if you look at Aviv Nevo, he did this for a structural model. He modified it to GMM instead of least squares. He picked a grid of 16,807 points. He had like 5 parameters that took 7 values, 7 to the 5th or something like that. So he had to solve his structural model 16,807 times. Well, I'm saying there's better way. If you'd use a finite mixture and you're using only 2 or 3, you only have to solve your structural model 2 or 3 times versus 16,807 times, okay? So I would say this is a profoundly computationally intensive and potentially inefficient way to do things. But, you know, these things, that people do these things. Now, let's go back to the random coefficient Slowjet model. Let's now look at just the binary case. So let me show you how well a small number of unobserved types works. So we're going to take this thing. We're going to have a random intercept and a random slope. Think about x as price sensitivity, and there may be correlation between tau 1 and tau of unknown form. Okay, and so this is the CCP as a function of price that is really of interest in BLP, and we're going to approximate this thing by this finite. So these are parameters now, and these are parameters. These are not fixed. We're not choosing these. We're going to let the computer fix this. So this is going to be like an ordinary parametric maximum likelihood problem. Now, furthermore, instead of constraining it, what I like to do, I like to solve things on. I can parameterize the choice probabilities in terms of, the probabilities add up to 1. So I'm just going to estimate gamma 1 through gamma r as unconstrained, and I'm going to use the multinomial logit model to give me the type probabilities. So now I can either do nonlinear least squares, where I have this choice probability. Theta now is the types. These are 2 by 1 for each type, and these are 1 by 1. So or I can do maximum likelihood. Okay, for this binary logit, and it's entirely parametric. But it's a flexible functional form because as I increase R, I get richer and richer approximations. Now, the asymptotic properties, let's just think about this first for nonlinear least squares. We're going to claim that the nonlinear least squares, the CDF is asymptotically for a fixed R. Let's fix R and just let the sample size go to infinity. What it's going to converge to is a CDF which is a function of the true CDF. So it's a misspecified model. If I fix R, I don't have it doesn't necessarily nest the true unobserved heterogeneity, but what's going to try to do is get as close as possible in terms of L2 distance. In other words, G of R, which is a function of G, is going to be the CDF that minimizes, it's going to be a finite mixture that minimizes this L2 distance between the true mixed CCP and my approximating one. And the way you do this is you take the sum of squares for a finite n and you add and subtract, which they cancel out, and then you realize that this is a residual. This depends on the true G. This is orthogonal to this. So when you take the cross product, they disappear, and this is the variance under the true specification, and then this is the specification error, and nonlinear squares is going to try to have the least misspecified model. It's going to try to make that as small as possible. Now, similarly, this goes back to an idea of Hal White in 1982, maximum likelihood of misspecified. If you fixed R for any fixed value and didn't, let it go to infinity, there's a Kullback-Leibler distance. So maximum likelihood is equivalent to finding a G of R, a finite mixture that minimizes the Kullback-Leibler distance between it and the true G, which could be 10, and here's the Kullback-Leibler distance. So they're kind of, if you actually calculate this, and I will do that in a minute, they're very similar. Least L2 and the Kullback-Leibler give you very similar results, G of R. So now, if you take the limit, if you say G prime could be anything, here's the identification. What you can show for this logit model is if the Kullback-Leibler distance between the true G and some other G prime is 0, the only solution is the true one. So that's identification. And same with L2 distance. If that distance is 0, the delta is the L2 distance, they have to be, so we have identification, and so, using Kiefer-Wolfowitz, we should be able to get a consistent estimate. But the idea is, I'm going to show now, is that recently derived error bounds of the approximation error of certain classes of functions by neural networks, that these approximation errors decrease to 0 very rapidly, okay? In other words, I'm not quite setting these to 0, but I'm finding if GR is very close to 0. Both of these are very close, and if these are very close to 0, I should be very close to G. Okay? Now, so let's just show you how this works. But, and the thing is, I can make these things very close to 0 with only 2, 3, or 4 points of support. So it's really amazing, right? And it's breaking recursive dimensionality. I could have 20 random coefficients or 5, and these bounds hold regardless of the dimension. Their dimension, normally for non-parametric regression, there's a cursive dimensionality. Doing a non-parametric regression for 5 variables, forget it. You'll need millions of observations to get acceptable precision. Here, I could estimate a 20-dimensional problem with essentially the same precision as I could estimate with 2. That's what the results, very, very powerful. So that's called, the computer science call that strong tractability. Okay? Now, once we can, if we fix that, then, we use this result, we're going to be able to get asymptotic normality for an asymptotic normality at 1 over the square root of n for this unknown function, and we're still working on this, but at the same time, so we're going to estimate this really, really well, even though we don't know this. We're going to get the CCP, and think about the CCP as the demand function. We're going to get the aggregate demand for the good really, really well. And it's going to be estimated with very little error. But at the same time, the estimate from the finite mixture is going to converge very slowly to G. So it's kind of a paradox. We get a really crummy, this is exactly what Hackman and Singer found, very crummy estimate of the true distribution G, but really good estimate of everything else. So why is that? How would that happen? Now, this is, there's a paper by Andrews and Isaiah Andrews and Anna Mikusheva. I think this falls in the class of weak identification. So G is weak, it's identified theoretically, but poorly identified. So let me show you a couple results. Let's see what I have. I have 20 more minutes, right? 25. First of all, let's just recall what a neural network is. A neural network is really just a nonlinear regression. There's a squashing function, sigma, like a logistic, and there's weights. So this is called the input weights. These are called the hidden units. R is the number of hidden units. W's are the weights on the output weights. There's an output bias and output weights, and then the inside there's an input, a hidden unit bias, and a hidden unit weight. So omega 1R. That's the coefficient on X, and that's the bias, right? So these are the parameters of the neural network model. This is a kind of single layer, the simplest textbook neural net. Now, the universal approximation theorem says, give me any continuous function f and any epsilon. I'll find a number of hidden units and parameters such that I'm uniformly within epsilon of the true function. So now you should think about, this will be the mixture model, and this is the true CCP. So it's kind of an easy translation to take this universal approximation theorem and say, well, F is the mixture of these mixed logits. This is going to be a squashing function, but now we're going to use a result, a very powerful result that we discovered by a guy named Mashkar. And his paper in 2021 is called Dimension-Independent Bounds for General Shallow Networks in a journal called Neural Networks. And what he looks at now, so here's the thing. The universal approximation theorem doesn't break the curse of dimensionality. In other words, if you use neural nets or deep neural nets, they just don't automatically break the curse. If F is continuous, but it could be really ugly with a lot of wiggles and stuff, and a lot of oscillations. In general, if you have d dimension, the number of hidden units will go up at the rate 1 over epsilon to the d power. So d is the number of covariates. So in 1 over epsilon, if you want epsilon small, like if epsilon is 1,000th, that'll be 1,000. 1 over epsilon will be 1,000, and if you have 5 covariates, it'll be 1,000 to the 5 power. You'll need a huge number of hidden units to approximate well, okay? But starting with Andrew Barron, who is at Yale, he said that there's some subclasses of continuous functions for which we only need a small number of hidden units. So the number of hidden units, the error goes down like r to the minus m. It doesn't depend on the dimension d. M is just some integer there. So Barron's functions were, so Mashkar is saying we're going to follow Barron. Now we're going to look at functions a little like this. There's a kernel, which is a squashing function. It's very much like our logit model. But then he allows for things that are signed. This mu is a signed measure, okay? But we're looking at a case where this is a probability measure is a special case of a signed measure can take negative. There could be negative values, right? Like a difference of 2 CDFs is a signed measure. But here we're just looking at a regular probability measure. So it's even got more structure than he assumed, which we think we can further exploit. But here's his result. We're going to approximate the function by, this is like a finite mixture. They're weights and parameters, they're the types for a number of r. So what he shows is the difference between any function f in this class and this finite mixture approximation the error goes down like a universal constant c times the square root of log of the number of hidden units over r to the s, and then this is called the total variation norm. That's going to be 1 for a probability measure. So S can be very large. It could be like 100. In other words, this is giving you a super fast rate of convergence, independent of how many x's there are. So this is this is like breaking the curse of dimensionality in approximating these functions. And so we're going to use this now for what we're going to show. Of F? What S is? Well, we're in communication with Mashkar now because he just says for any S. Well, that doesn't make sense to me because, well, if I let S go to infinity, then this is always 0, right? And think, well, then, you're like with only R equal 1 or 2, I can perfectly approximate. So S is related to the smoothness of this G function, which in our case it's infinitely smooth. So this S depends not on the dimension, but the smoothness. But since it's infinitely differentiable, this is one of the things we're still trying to figure out what that exponent S is. So, no, it's R to the S power. So like if this is R squared, then the error is going down like square root of log of R over R squared, right? Really, really fast. So, rather than try to play theorist, let's do an example, okay? Let's try his theorem out by, things I can do. I can program this up. In fact, the code that I'm going to show you now, it's MATLAB code that you can run. So these figures have been done by Matt. So what I'm going to do is going to take a binary logit model, and I'm going to generate the random coefficients by a mixture of two normals, all right? Each normal is a bivariate normal. So I'm going to take a mixture of bivariate normals and generate so their true distribution is their correlated coefficients for the intercept and the slope. And we're going to see, can we recover that mixture of bivariate normals with this finite mixture, right? So we're going to be looking at how well I do this, and then here's the overall CCP. We want to say, how well does this estimated CCP, so G of R is the finite mixture implied by that's the CDF. And so now we're going to see how well do we do. So here's the first one. We start out, you always start out with one type, no heterogeneity. And so the red line, the blue line is the true. This is the true, like, CCP. You can think of this as the demand function. Think about X as price, downward sloping, nice and smooth. And if I only have one type, we have specification error, it gives me like a line, okay? Now what happens, and look at the L2 distance, it's the sum of squared errors, or the absolute error is 0.04. What happens when we have two types? Bam, like I've nailed it, two types. Now, the way you should think about why is it nailing it, see, in other words, the blue and the red line are totally coinciding. The difference, the Kullback library distance is 0.001. The maximum error is like 4/10,000ths over this interval. Okay, now let me tell you the dashed lines. When you solve the finite mixture model, we can think about the estimate of the CP, the population, is a linear combination of basis functions. This is a basis function. It's actually a convex because they're positive and they add to 1. So we're taking a weighted average, and these things are now. But the thing is, they're not pre-specified basis functions. The neural net has cleverly selected the basis functions to be the best of it. It's adapting. See, when you do Chebyshev polynomials, the Chebyshev polynomials don't depend on what you're approximating. You have to say, and then you're using just the coefficients to get a good approximation. The neural net is choosing these to kind of twist the basis functions to get the best approximation. So let's go back and look at this. Yeah, it chooses one basis function that's almost linear, and then the other one, it's got a lot of curve, and the weighted average of these is almost exactly equal to the truth. All right? Now, by the way, I'm now I'm looking at the Kullback library distance. So this is like I'm looking at the pure approximation problem. It's like what happens to maximum likelihood when you have infinitely number, so there's no estimation noise. I've just kind of taken that out of the question and just looking at how well can this finite mixture approximate using the Kullback library as a measure of distance. So then what happens if you go to 3? Now it's got a crazy type that is upward sloping, right? You might be disturbed by that. It hardly improves the fit at all. And then I go to 4 types, and you start getting all these different lines, right? And some of them start to look like almost collinear, right? These two lines are hardly any difference. So what happens is that what you get is, you're starting to get numerical error, right? You have two types that are almost identical, and the probabilities are, and it almost doesn't matter, right? You can combine them into one type. So what's happening now is my computer is only finite precision. At some point, when I get before 5 types or 10 types, I'm running into machine noise in what this is doing. I mean, an infinite precision computer might get something different, but my computer can't tell the difference, right? Yeah. Yeah.
Can you have another combination that give you the exact same solution?
Yes, and I'm going to show you that in a minute too. Yeah. In other words, when I run this, I get different results each time I run this. The thing converges. If I have slight errors in where I started, it converges to the same. The errors are driven to 0, but the functions that come out are a little bit different, and sometimes a lot different. And so what's like, we have a flat objective function. And that's another indication of the weak identification. If you have a likelihood that's almost flat, you're going to say, I can't identify this parameter, right? That's what's happening here.
So
Yeah, exactly. The types are not being determined, you know, and another way is I'm going to show you the distribution is not well estimated, okay? So I go up to 10, I go to 15, 20, and I stopped at 25. Here's 25 types, right? A real mess, right? You know, and you would say, wow, there surely must be 25 types. But good luck on trying to, you know, determine what those 25, and, you know, are they reasonable? Now, I'm going to show you some moments of the bivariate. It's the mixed bivariate normal. And so I'm going to show you how these lines here, is as I increase the number of types, here's the true, let's see. There's a mean slop, approximate mean slope. That's the x coefficient. It's right here. And here's the error. And you know, as I'm increasing the number of types, it's not really converging that fast because it's just hard to estimate this thing, right? So it's, you know, this is the crudest thing of a bivariate norm is just get the moments right. And what happens here? Well, the estimation got stuck on like a local optimum. And I just left it in just to show you what can happen. And then, you know, it's way off and then it goes back down, but it's wiggling because you're just at machine precision. It's just has a real hard time really nailing that moment. You know, here's the standard deviation of the intercept. You know, it's getting close, kind of, but, you know, not in a nice monotonic way. Here's the standard deviation of the slope. That's getting it a little better, right? And you would expect that because the slope has x variation, you'd expect that's easier to identify than the intercept. And then here's the correlation between the intercept and slope. It's non-zero here. It's kind of, you know, minus 0.17 or something. And, you know, it's kind of pretty far off and kind of going there, but it's zigzagging back and forth. Yes? Yeah, yeah, all of these things are, yeah, that's when I solved it like for 7 types, and at 7 types, all of these things went haywire together.
And is that determined by the initial condition?
Yeah, it just, you know, it's just very sensitive to your initial condition, and that's why, you know, when people use stochastic gradient descent, what they're doing is adding in additional noise, the neural networks, because they get stuck at these things all the time. Now, when this got stuck, it's still, the criterion was really good. It was a good fit. It was like almost a perfect fit. It just was stuck far away from what we know to be the truth. But if you were to look at the criterion, you would say, hey, this is a great fit. You wouldn't know. Now, let me show you the actual distribution. So here is the marginal distribution, the bivariate normal of the intercept, and then there's going to be one for the slope, the x coefficient, and there's the true one. And if I have only one type, obviously what it's doing is setting a beta, which is kind of in the middle of that distribution, right? There's just one point of support. Now we go to 2 points of support. What it does is put a little bit of mass right there, okay? Now we go to 3. Now it puts that couples step, and you see it's kind of converging. 4, 5, 10, 15, 20. So it's kind of getting there. But if you look at the maximum difference, even with 25, the maximum difference is 0.2. It's a big difference. A little bit disturbing, right? And what about the slope? Does that do better? Because there's that's got the price identifying variation. Here's 2, 3, 4, 5, 10, 15, 20. Not that much better. So the way I think you think about this is with a neural net, we have an objective function that's very flat around, in this function here, the true solution is at 0. But if you could see this, it's really, really hard. It would be if I gave this function to you as an optimizer, say, what's the optimum? You would, and I didn't tell you that the true solution was 0, you could be anywhere in this range, right? So that's a poorly identified objective function. That's exactly what's happening in a finite mixture model, but in a much higher dimensional space. There's a big region of coefficients where you can't tell what they are. Okay? Now, what's interesting paradox though, so you'll find this if you compute the information matrix. Really, what you do is the information matrix is a parametric model. The standard errors of the covariance of the parameters are given by the inverse of the information matrix. But on the other hand, if we say, you know, the parameters of this are like the standard errors are huge because the information matrix is almost singular. Its eigenvalues are getting really, really small as I make the number of types big. But when I use the delta theorem, when you use the delta theorem, you get this quadratic form. You have the gradient of the CCP times this inverse, which is very, very big matrix because it's inverse of a matrix with eigenvalues very close to 0 times this. This actually is small. So how can that be? How can this be huge, but this is small? What happens is that if you, what's called the singular value decomposition of this information matrix, there's going to be eigenvalues, eigenvectors corresponding to the eigenvalues. It turns out this thing is magically orthogonal to all the eigenvectors corresponding to small eigenvalues. So they're just, all the noisy part is completely killed off, and the variance of this only depends on the parts of the parameters that are very well estimated. So that's how I'm able to really nail and very accurately estimate this, not only at pointwise, but for the entire, you know, uniformly as an entire random function. So I get a Gaussian random function estimated really well, even though this function here estimated terribly. Okay, let's go to one more example. Now, what happens? So that's depressing in some sense, right? If you like to observe, you like unobserved heterogeneity. But now here's the hopeful part. Well, there is a hopeful part of what I just said too, is I can get the CP, well.
Sorry,
yeah.
I don't know if you built that intuition of this, but the function you showed us, because you were loading, using logic, it's so
Yeah.
smooth and
Yeah.
the problem is that it's too smooth, it's too predictable, right? And so can you relate that to, because you showed us these indication results based on the derivative of this function.
Yeah.
And in some ways, the derivative of the function is basically the same almost every x. But if you were using a funkier function for the demand, which like the slope changes all over the map,
Yeah.
then you wouldn't have that problem. So I'm wondering if this problem is because we're using in your mixed logic model.
Well, the smoothness of the logit, yeah, I mean, the derivatives get kind of worse. As you take higher order derivatives, they don't stay small, actually. I calculate them out to 5 derivatives.
They're really similar across x's.
Yeah, exactly. But that's just in the nature, you know, the finite mixture model is exploiting this, you believe in the logit model, the finite mixture is keeping that. That's C infinity too. So that's really driving everything. It's really the smoothness. If you weren't confident about that, then things could well be a lot worse than I'm showing you. Okay, but we use random, we believe in logit and we use random Cohen's logit. Yeah. Now, let's take a panel data. So let's now assume we have binary panel data. You have binary choices. You see each person t periods. The x's are independent. So, there's like t times your, deciding whether or not to buy at different prices for each person I. People are independent. And so what we do is, the first thing you might say, what's fixed effects? If t is pretty big, I can write an individual likelihood for each person I, and I can estimate their tau person by person. Okay? Now, if t is actually going to infinity and n is going to infinity, then here's how you can recover G really well. You estimate everybody's tau person by person, and then you form an empirical distribution function. So these are using the time dimension. This is done by averaging over the cross-section of people with their estimated taus. So now this is an empirical CDF, and as long as the error in this is negligible, this is converging at square root of n. That's empirical process theorem. In other words, you can nail an empirical CDF nails the true CDF in any dimension. So this just tells you if you have a large number of time series and in limit it goes to infinity, then there's no problem. And that's kind of intuitive. That's as you'd expect, right? So that's not maybe surprising. Now, let's talk about the case in the middle where we have a fixed t. Now, cross-section is t equals 1, but let's suppose t is not going to infinity, but it's bigger than 1. What you can show is that the information matrix, when you have more time periods, is bigger than the information you only have one person. That's kind of obvious. So that means the standard errors are going to, because you're inverting the information matrix. So if this is more information, the standard errors with panel data are going to be less. So how much less? How much bigger? How fast does this thing get big with t? So effectively, another way to think about it is with time series panel data, the objective function becomes less flat. The Kullback-Leibler distance gets more and more curved as t gets big, and that curvature shows up in the information matrix. Now, what I'm going to do is show you another Monte Carlo example. Now, this is actual with real noisy data. I simulated data from the same bivariate normal for 5,000 people, and I'm going to have 50 time periods. Now, 50 for like some lab experiment, that's not a crazy large number, but it could be realistic in some cases, 50 observations. And 5,000 isn't a huge number. The question is how well does this do? Now, here I'm going to estimate empirically the number of types with model selection. So there's something called AIC, Akaike information criterion. So I'm penalizing number parameters. So I'm taking the negative 2 times the log likelihood and then adding on a penalty for the number of parameters. And then BIC, the Bayesian, is taking the log of the number of parameters times the number of parameters estimate, 3r minus 1. So why is it 3r minus 1? There's 2 parameters per type, intercept and slope. That's 2r. And then we need r minus 1 for the probabilities of those types. So that adds up to 3r minus 1. So here's the likelihood. Obviously, if you don't penalize, the model always just gets better as you add more types. But look at how concave that is. This is the general result. It gets better and better and better, but at some point, 5 or 6 types, it's just getting very flat. Now, what about the model selection? Here, I can select a much bigger model than you can. With the time series dimension, BIC is minimized at 17 types, and AIC is 21 types. That's much bigger than I ever see in real data. Well, so I don't know. Has anyone seen a model where there's 21 types estimated? Huh? Yeah. Oh, it does? Yeah? 24, okay. And do you have panel data? All right. There you go. Proof, QED. All right. So here's the same thing. Here's the moments of the mean intercept. Here's the X coefficient. And now they're actually kind of converging much better. And they're kind of close even in the range of the selected models, which is like right here. Now, here's the CCPs. This is one type, same as we saw before. Now, remember, this is the estimate with data. There's noisy data. The curve looks really smooth, right? Because, it's logit, it's parametric. Now here's 2 types. It's not quite nailing it as it did last time, but it's taking a convex combination of these two logits. Now we go to 3, 4, 5, and now we're almost dead on. 10, 20, and look at, we're almost dead on. Yeah.
So if you have this, like the algo kind of rate when like your explanatory power is not increasing that much, like shouldn't you be like Occam razor with like ignoring the more times next to 6 because you can explain most of the variation with the 6 and the 24 are only giving you like a minor improvement?
Yes, that's what the concavity of the likelihood shows. It shows you the marginal value of these extra types is really falling off very fast.
So why would you ever go for 21?
Well, that's what the model selection says. And, if you go back here, what you want to go to is looking here. It's still kind of improving until you get into the range where some of these moments are. Now, there's another feature of the model that you don't see here that I'm going to show you. what happened is when you have panel data, someone with, like, for instance, a high desire to buy the good, like suppose it's a car, you know, I want to buy it, and they're going to be persistently buying the item a lot. They have a strong preference. Someone with a low preference will be very little. Well, if you only have an average type, you're trying to mix between these two. But once you have two types, the panel can say, oh, there's this type that will persistently be buying, and then there's this other type, and by taking a mixture, it fits the data a lot better. So what's happening is adding more types is picking out more dynamic patterns of how people are, it's dynamically seeing clusters in the data, and it's approximating with these types and being able to pick them out, okay? And that's where, even though the CCPs aren't changing that much, the ability to fit is really improving in a way you can't see here with the more types. Now let me show you the distributions. Here's one. This is the intercept again. 2, 3, 4. So this is starting to look better. Look at 10. That's just materially looking better with real data. That's with noisy data. Here's 20. Here's 25. Much better, right? What about the intercept? 1, 2, 3, 4, 5, 10, 20, 25. Now, still big. The maximum difference is 0.12, but a lot better. So I think I'm over time, so I'll just stop there. So the thing is, it's not hopeless, right? You know, but you need panel data. Panel data. Okay, thank you.